So that I'm also around.
Yes.
But looking forward.
Anish, let me know whenever you want me to start.
Yes. So welcome everybody again for our second talk of the day. And we have Dr. Mustafa Amin from Rice University, and he's going to talk about how light can dark matter particles be. So maybe I'll send you a reminder when 5 minutes are left.
Thanks so much. Thanks, Anish, for organizing, and thanks everyone for attending. I see some familiar names as well. Hopefully, I'll get a chance to say hello after the talk a bit more as well. Okay. So what I want to tell you today is try to answer this question on the slide, which is how light can dark matter particles be? What is the lower bound on their mass? And not to keep you in suspense, but the answer, according to us, is that dark matter particles cannot be lighter than 10 to the minus 19 electron volts. The talk today is structured in the following way. So first, I'll tell you about how Mehrdad and I, who is the first person on this slide on the top, arrived, what was our logic behind arriving at this conclusion. But as we thought through this, there are a lot of phenomenological implications that were part of this construction. So we've been working hard on that, and I will also present to you the work related to that, meaning what are the consequences for small-scale structure in dark matter that arise when we started thinking about the lightest mass that dark matter particles can have. So the first part of the talk will be based on work with Mehrdad as well as with Xiang Ling, who's shown here. Then I'll tell you a little bit towards the end about the paper that just came out today. This is with Mehrdad as well as with Sendelos. And if time permits, I'll also tell you a little bit about ongoing work with Simon Mai. All right, and please interrupt me along the way if you have any questions. Happy to answer as we go. Okay, so first, let me tell you about this bound on the mass of dark matter particles. And I'll start with a bit of motivation for how we got to think about this and so on before getting into technical details. So as you all know, we think dark matter exists, but we don't know its microscopic nature. What I mean by that is that we don't know, for example, what the mass of the constituent dark matter particles is, nor do we know what its spin angular momentum is. For example, dark matter could be a fermion, it could be a boson. If it's a boson, it could have spin 0, 1, 2, etc. Its mass also has a huge range, right from 10 to the minus 20-ish, or if you believe us, 10 to the minus 19 eV, all the way up to Planck scale for fundamental particles, and even bigger if you include composite objects. The reason, of course, why we have such a huge range for mass is because gravity is sensitive to mass density, not to number density. So there is a huge range of masses of particles that's allowed. But it is not as bleak as it seems here. Right? So once you start thinking a little bit further, you get some constraints almost immediately. For example, if you say that the dark matter particles, you make an assumption that the dark matter particles are fermions, then Pauli exclusion tells you that their masses have to be bigger than roughly 100 electron volts. It's just a statement that you know the mass density of dark matter, and you can't pack too many of them together because they're fermions, and that gives you a limit on their mass, which is about 100 eV. So that is a huge reduction in this range once you make this assumption. However, if you continue to allow the particles to be bosons or fermions, then this limit goes away. In particular, for bosons, you can have very light masses. And if you go to this light mass regime, that is masses much below an electron volt, then what you find is that really it becomes much more convenient and physically interesting to think about these things as a classical field. Why? Because when you make the masses sufficiently light, the de Broglie wavelengths of these particles start to overlap, and at very low masses, they are so overlapped and the occupation numbers are so high that it becomes rather natural to start thinking about them in terms of a classical field. So this regime is often referred to as wave dark matter. It's not really new. We've already been thinking about these kinds of things when we were thinking about axions for a long time. But it is this regime, because I'm trying to put a lower bound on the mass, it is this regime that we'll be interested in, and we'll be talking about bosons from now. So again, we're going to be in this regime, and it's going to be in this wave dark matter regime because we're in such light masses, and we're going to be talking about bosons. And I'm going to tell you what the lower bound on this mass is. But something that's sort of interesting is when thinking through this, you also realize that it also gives you an upper bound on the constituent dark matter particles. Because the same kind of thinking tells you both. But I'll explain this towards the end, why this is both. Okay, so now coming to sort of the key thinking about this bound. So here's sort of the main slide without the logic yet. The key statement I want to make is the following. If you produce dark matter in the early universe in such a way that the energy density of dark matter is dominated by sub-Hubble field modes, then the claim is that there is a bound on the mass of dark matter particles, and that bound is 10 to the minus 19 eV, meaning they cannot be lighter than this bound. Let me sort of unpack this statement a little bit. So look at this sort of cartoon that I've drawn. This, let's say you are sometime in the early universe, and there is a scale here, which is a horizon scale. I'm saying that in all of these models, you have to imagine that the field fluctuations are large on the scale shorter than the horizon. In that case, there is a bound on the mass of the dark matter particles. Again, examples of axions with QCD phase transitions after inflation would have this structure in them. However, axions that are produced, the vanilla models of axions that are produced during inflation with a homogeneous mode would not have this feature. In terms of the power spectrum, the field power spectrum will be peaked on some scale that is sub-horizon, and the way we are thinking about it, it's also, because it's dark matter, at some point it is also non-relativistic. So it's a peak spectrum of the fluctuations of the field, but not of the density. But again, this is too much detail perhaps. The main point is, if dark matter density after production in the early universe is dominated by sub-Hubble field modes, then there is a bound on the mass. You might say, oh, but is this too special? I will claim that it's not. And I will also say that the number, by the way, 10 to the minus 19 eV, for other reasons, is generally true, even for other mechanisms, even for homogeneous field modes that you can solve. Okay, so here's our logic. Here's the argument. So suppose you start with this assumption that dark matter produced in the early universe is dominated by sub-Hubble field modes. Then there are two phenomenological implications. One, in the density power spectrum, there is an enhancement on small scales. This is initially a white noise type of excess in the early universe, and then it evolves. And then, at the same time, there is also a free streaming suppression of the adiabatic part of the density spectrum. The fact that both of these two effects, this enhancement due to white noise and this free streaming suppression, both of these are not yet seen in cosmological data. For example, based on Lyman alpha observations up to 10 megaparsec inverse, the fact that these have not yet been observed, this is what gives us a bound of 10 to the minus 19 eV. So again, just this assumption of being dominated by sub-Hubble field modes gives these two implications. And the fact that they have not been seen gives us a bound. So any questions at this point before I go into a little bit more detail? Okay. So just let me put the bound that we have in the context of other bounds. So for example, here is sort of an incomplete list of a large number of works trying to put a bound on the mass of dark matter particles at the lower end. They are from very different sets of observations, comes with different assumptions, but you can see where roughly the numbers lie. We are also providing a bound in this sort of a domain, but with the assumption that we are making. So you shouldn't just be comparing this and saying, oh, one is better or worse in that way. I will say that this bound in particular by Dalal and Krautsov that I've highlighted here, that is similar, and that actually doesn't even rely on the assumption that we have made. So regardless of the assumption you make, I think the bound of 10 to the minus 19 EV is strong. It is still there. Okay. So let me give you a little bit more detail in this context. So first question is, I said that, I'm making an assumption that dark matter in the early universe, especially when it has become non-relativistic, is dominated by sub-Hubble field modes. That is, a power spectrum of the field, for example, it could be a scalar field, but doesn't have to be, has this kind of a shape that I've drawn here. When does this happen? In the case of inflationary particle production for dark matter, this can happen, for example, with dark photon dark matter that naturally has this sort of a peak spectrum. For scalars, it can also happen. It can happen in certain models of, I think, with non-minimal coupling, or it can, if you arrange it right, in certain even models of QCD axions, it can happen, but you have to be a little bit careful with those there. For post-inflationary production, this is very generic. Right? You produce dark matter from phase transitions, you produce, for example, from the QCD phase transition, or you produce it, say, from transferring energy from one field to the other, for example, from preheating or from tachyonic resonance and things like that, or you produce dark matter from strings. All of these are what we refer to as causal mechanisms, meaning the correlation length is smaller than the size of the horizon. All of those cases will naturally produce a peak, which is in the field, which is on sub-horizon scales when they're non-relativistic. So my claim is that at least for post-inflationary production, this is very generic. For production during inflation, not all models will have this, especially a minimally coupled very light scalar will not have this feature. By the way, this peak spectrum, even if you are thinking of particle dark matter, like standard WIMPs, you will see that some of these effects that I'm talking about apply to those, but they are not so interesting as far as observations are concerned, the effects I'm talking about for those cases. Okay. So now let me go into telling you. So hopefully I've convinced you that it's interesting to think about this because this is a large selection of models that have these features. So how do you get this? First, I'm going to talk about why do you get this white noise? Why do you get this excess of perturbations on small scales? So this actually is quite simple, okay, in our view. So you produce dark matter with a finite correlation length, as a result of which the density fluctuations beyond a certain length scale will not have any correlations, as a result of which the power spectrum should be white noise, meaning it should have no correlations. So that's essentially it. If you want to actually go through the calculation, you can just take your field's power spectra, you can calculate the density spectrum. The field is peaked at some lengths, some wave number here. If you ask questions about what the density power spectra looks like on scales small compared to the peak, then you will naturally find that the power spectrum is just flat, meaning this P of delta is flat, and flat in P of delta means in k cubed P of delta, it rises as k cubed, and that's what white noise is. So just this causality type consideration that is finite correlation length will give you this white noise feature that I'm talking about. So it's very general in this sense. And on the left-hand side, you are just seeing a realization of such a field that is produced with a finite correlation length. You can see that on scales large compared to the size of these blobs, it looks like randomly distributed, Poisson distributed blobs, as a result of which you get this white noise feature. What is this K white noise that I've written down? It's basically when you do this integral over the fields, it's a constant, and this is characterized as that constant. right there. So it's nothing more than that. So it just scales what the amplitude of this k cube line is in this case. Now, you might say, well, this is a k cube spectra. I already know from CMB and so on that we have a roughly scale invariant spectrum. How did this connect with that? Well, if you go to larger length scales, okay, you should match on to the usual adiabatic almost scale invariant spectrum. And that does indeed happen. You should think about this at on large length scales. You're born in existing potential wells set up by inflation. That is, there are already existing correlations on large length scales, as a result of which the same dark matter already has this scale invariant density spectrum. So the whole picture is that you have this almost scale invariant density spectrum on large length scales. Then on short length scales, you will have this k cubed rise, which will then get cut off at roughly of order k star. When you try to look at this spectrum at the time of matter radiation equality, then because of the growth during radiation, the small growth during radiation domination, then you have the scale invariant part of the spectrum rises up to an amplitude of about 10 to the minus 6 on these scales, whereas this one, just as I'll argue, just remains as it is from the time of production to this point. So this one is k cubed, this is 10 to the minus 6. You can equate the two and you will find the location that is shown by this connecting line here, the location where they intersect. And you will find that that location is roughly, because this is 10 to the minus 6, you have to take a cube root of this when you equate those two, and you will find that this location where they deviate from each other is roughly 10 to the minus 2 k white noise. So the scale where you see the deviations is a factor of 100 larger length scale or smaller wave numbers than the scale that appears in the white noise. So that's where the deviations should appear. And in these models, and the other ones that I've mentioned, you can start looking for them there. So that's one aspect of this, right? And again, we're not the first people to point out that there is this white noise access that can happen in certain models, but we're claiming that this is quite generic in post-inflationary production. What now about the second feature, right? And this is something somewhat that adds another interesting element to this. The second part is that if you produce fields with a finite correlation length, they naturally have the spatial variations. Now, as soon as you have these spatial variations in the field, when we think about fields with spatial variations, that means that the fields do not have zero momentum, meaning the fields have, if you think in terms of particles, the particles have some velocity. If you have a perfectly homogeneous field, you should think of them as a collection of almost perfectly cold particles with zero velocity. But these fields with gradients have characteristic velocities now. And the characteristic velocity is determined by the peak of this power spectrum, k star, and the mass of the particles. So these particles that are born, or these fields that are born, are moving around. That is, they have a characteristic velocity, as a result of which they move around and they want to wipe out existing correlations. So the pictures that you're seeing on the bottom is actually from a full 3+1 dimensional simulation. We start with some density fluctuation. As you can see large length scale fluctuations, which are dense. The yellow is denser, blue is less dense. You can see that there's some variation, but because of these fields moving around in the early universe, because of their velocity dispersion, when they're born, they tend to erase those large density fluctuations. So that's what you're seeing the time evolution here of. So the very thing from causality that produced that white noise also comes with some velocity dispersion, and that velocity dispersion tends to wipe out existing correlations. Notice that I'm being careful to say that it's not wiping out white noise, it's wiping out existing correlations. White noise is no correlation, so it won't wipe them out. And this is something that's slightly counterintuitive, so I'll spend a little bit more time discussing this fact. Okay, so here is again a picture of this global picture of what's going on. So you have, by the time of matter radiation equality, you will have the scale invariant part, roughly scale invariant part of the spectrum. Potentially, you will have, depending on the parameters, you will see this free streaming suppression in the power spectrum because that I'm showing in orange. And then there is this white noise part that's sitting there. What determines the scale at which this free streaming suppression happens is really determined by the scale K star, that's the amplitude of the field power spectrum, where it's peaked, as well as the mass of the particle. Okay, it's the distance moved by the particles by the time of matter radiation equality from the time of production. And this wave number scale is just the inverse of that length. And as you can see, the ratio of K star and M, which is like a velocity, that's what appears in that expression. So that's what determines the scale of this suppression. But again, notice the K cube part is kind of just sitting there. Okay, so how does this happen? So let's go and dig a little bit more first into the physics of both of these aspects, that the K cube part up to equality essentially doesn't evolve. However, the adiabatic part can get suppressed in this case. Okay. So let me first try to convince you, of course, when we wrote the paper, we did it analytically first, but then we also did some detailed numerical simulations, full field simulations, just confirm what we had done. So I'll first show you the results from the simulations and then tell you in somewhat reverse order what the intuition was about why this had to be true. So this is a toy simulation. Just for the purpose of illustration, I can also show you the detailed realistic ones in a moment. So what you're seeing on the right-hand side is the vertical axis is the density power spectrum, horizontal axis is wave number. The flat part is a correlated part. You should think about this as the adiabatic part of the spectrum. This rise that you see is the white noise part of the spectrum, and then it gets cut off somewhere. This is how it starts initially. Now I'm going to run the movie forward, and the gray part is just maintaining that initial spectrum. And you notice that as time goes on, this correlated adiabatic part of the spectrum is getting erased. That is, it is going down. However, the white noise part remains. Indeed, you are revealing more and more of this K cube uncorrelated part of the spectrum as time goes on. So this is free streaming doing its thing, removing the correlated parts, because it's removing existing correlations, and revealing more of the white noise part. Again, just a bit more, let me see. Visually. First, I'm showing you the let me go back. I'm showing you the evolution of the density on one side and the power spectrum on the other. The sort of light yellow band is meant to indicate when I'm showing you the density field, what am I filtering? Meaning I'm looking at very small length scales. So there you don't see this effect because it's not visible on the density slice, because I've not done any really filtering of the small scale modes. So they dominate because that's where the spectrum is peaked. But now when I look at small lengths, at small wave number or large length scales, this is a correlated part of the spectrum, then you are able to see this effect of free streaming. Free streaming is, it grows slowly, so it takes a while, and that's why you're seeing this slow behavior. But I'm just going to drag this mouse quickly, and you can see that initial perturbation disappearing. Notice that it did not erase small scale power, right? It only erased the large scale power in the system. So again, just trying to convince you that this effects we are talking about are real. One way of intuitively thinking about this in the context of wave dark matter, which hopefully will help if you are used to thinking about just particles, is think about these small scale fluctuations, which are essentially de Broglie scale volumes. What I mean by that is you take the de Broglie wavelength of the field at that time, which is determined by K star, and you calculate the mass within the de Broglie volume, which will be much larger than the particle mass. But you think of this entire thing now, entire de Broglie volume that I've indicated by the dash thing, as a quasi-particle. And you think of these particles as now your fundamental units. and you try to ask what is roughly their motion during this time. It's not that these particles are moving, but they're appearing and disappearing in such a way that you can think of these particles as moving around. So if you think about it this way, that is, you think of it as point particles representing quasi-particles, then here's what white noise is doing, what the evolution of white noise looks like under free streaming. On the left-hand side is a Poisson distribution of these quasi-particles. If you take the power spectrum, it look like white noise because they're just Poisson distributed particles. Now, if you randomly move these particles around under free streaming, even though the particles have moved around, statistically, it still remains white noise. It doesn't change. It still remains Poisson distributed. This is why white noise remains white noise under free streaming of particles. If you don't have correlations before, you can't generate correlations because of just free streaming. On the other hand, if you had correlated density fluctuations, such as adiabatic fluctuations, so large densities here, low densities there, then random motion of particles because of free streaming will erase those existing correlations. You will take some density fluctuations and make them uncorrelated Poisson distributions, as a result of which you are taking away power from correlated distributions and converting them into white noise power spectrum. So this was sort of the intuition that we had when we wrote those things, but of course I showed you the simulations that justify this for wave time. Okay, so let me summarize what I have said so far in terms of the argument. Now, hopefully, I have provided with you some more detail. So if dark matter is produced with finite correlation length, this will mean that the energy density is dominated by sub-Hubble field modes. In that case, you get both a white noise excess, which will lead to some deviation from the scale invariant spectrum at roughly 10 to the minus 2 times this k star, the scale where the white field spectrum at peak was k star. At the same time, it will also give you a free streaming suppression, and that scale, because this field has momentum, so it will move around, and that gives you a free streaming suppression of the adiabatic part. That depends on both k star and the mass of the particle. Now we make use of observations. That is, we look at observations of the matter power spectrum, and we find that there are no deviations from the scale invariant spectrum up to 10 megaparsec inverse co-moving. So we're just using that length scale, right? That's it. And the fact that we haven't seen that, that means that both k deviation and k free streaming must be larger than that length scale. As a result of which, the fact that we haven't seen this deviation now gives us a bound on the mass of the particles. The interesting thing here is that k star is a model-dependent statement, right? It depends on what was the thing that produced this dark matter, what was the process. But the fact that we don't see these observations and both of these features are not seen allows us to not have to worry about k star, meaning we can use observations to get rid of k star and give you a bound on the mass independent of k star. So the mass is an independent statement. It says that it has to be larger than 10 to the minus 19. Again, if you sit down and just say k deviation is larger than 10 megaparsec inverse and k free streaming is larger than that, then this is the only conclusion you can reach based on. Okay, so that's the entire argument. To convince you that this is model independent in terms of sort of details that you might have, let me just give you a very rough guide to this. For example, the initial power spectrum, I just was drawing it so far. Suppose you make it with some different power laws, right? Q to the nu as a rise and Q to the alpha as a fall of this power spectrum. You plug that in to a framework and you try to ask, okay, what is the bound that you get on the mass? You get roughly 10 to the minus 19 EV with some coefficients. We shouldn't really worry about the significant figure in front. They are roughly the same number, regardless of what sort of nu and alpha, at least in these domains that we have varied them are. Roughly speaking, you just can't make this lower part too shallow. but it's all the same number. Right. Okay. You can now also ask the question, why is this? I've got a bound on the mass, which is 10 to the minus 19 eV. But for people who have worked on warm dark matter before, they're used to seeing numbers like a few kilo electron volt. So what the hell is going on? Why are we getting such a weak bound compared to 10 kilo electron volts? The reason is that when we are putting bounds on warm dark matter, we are assuming thermal production, essentially thermal production, which means that there is a connection between the temperature at which these things are produced and the mass, which is inbuilt there. So that's an extra assumption. That's why you are getting a strong bound. However, if you don't make that assumption, I believe this is the best you can do. And you can look at some recent work by my colleagues as well on trying to allow for non-thermal expansion history, non-standard expansion histories, and so on as well. Okay, so let me just quote a couple of strengths. I think if you assume this is dark matter, which means it's weakly interacting with itself, I think this is pretty general. It doesn't have to just be scalars. It can apply to scalar, vector, tensor dark matter. I claim that it's also strong. If this kind of warmth, meaning there is power in some high K modes and not just in the zero mode, then this bound will be stronger than the usual cutoff in the fuzzy dark matter power spectrum that people use. So this bound will be stronger. That's why it's stronger than 10 to the minus 21 and 22 eV that we are getting. Also, you will find that if you work through it, you will find that the bound on the mass will improve as the observational scale improves. Meaning as you go make observations of the power spectrum on smaller length scales, the bound will improve quadratically with that length scale. So we expect this to improve quickly in the coming years as well. So that's exciting this way. So that's sort of where we are at in terms of this first part of the talk. And I only have 5 or 10 more minutes. I'll move to the second part quickly. But what I want to say is that this we are reasonably confident that this is where we are at. There is a lower bound on these particles, and of course there will be ways that maybe there are models that escape this bound, and I'm very happy to sort of hear about those things that escape these sort of considerations. But at the end of the day, one of the things that I always think is bounds are all wonderful, but what you really want to detect dark matter, right? We want to know what it is. So all of this phenomena that I talked about this extra white noise power, this free streaming suppression, those are also features, right? So those are features that we can look for in the data. So the next thing I wanted to do was to take these things and try to look for how can we look for these features in existing data. And that's what we've been working on recently. And there are lots of interesting things that's happening. Okay, so there's extra power on small scales. We found that the things that we were talking about not only turns out to apply to these light dark matter, but applies to essentially any form of dark matter, including, for example, primordial black holes. It applies when you think of dark matter it being constructed out of solitons or of mini clusters and so on. So there's lots of things that came out of this. And so in the last 5 or 10 minutes that I have, I want to just give you a flavor of where this is headed in terms of the features we can look for now beyond this bound. So one of the things that we qualitatively expect, and this is what the bound is based on, is that after matter radiation equality, the power spectrum essentially grows just proportional to the scale factor squared, meaning the density fluctuations grow just in the normal way, like cold dark matter, up to some gene scale, which is right here. So this whole thing this is the adiabatic part and the white noise part. The white noise part didn't grow much during radiation domination, but after matter radiation equality, it just grows like regular cold dark matter. But of course, we appreciated that there is a gene scale there, it's warm, so it can't grow up to all length scales. So this is what we had used in the bound, but now what we wanted to do was understand precisely the shape of these genes cut off, which we had not provided in the paper. So that's where we were headed next. And this paper that came out today, we thought it would be short, but turned out to be a bit long. So apologies for that, but it's quite general. So I hope you try to read through it, at least the summary part of it, which is at the beginning of the paper, to see what's good. So we worked through that, but let me just give you the punchline that, let me skip this and tell you what this current paper is about. So in this paper, what we found is, this is the paper out today, that we can do this calculation very carefully by starting, we want to calculate the behavior of the power spectrum, the adiabatic, and the part related to white noise. Even though you can't, if you want to do it analytically, it's a bit non-trivial. So we started with a truncated BBJKY hierarchy. We then realized that if you want to understand the density power spectrum, you have to worry about the two-particle correlation function in phase, or two-particle phase-space distribution. And so this becomes a PDE for that object, and you have to solve it. And that's what gives you the evolution of the density spectrum. This calculation doesn't really rely on it being wave dark matter. It applies to particles as well. So as long as the finite number densities and warmth are relevant, this calculation is correct in that domain. We provided an analytic expression. Again, I don't expect you to read through this, but the top line is the evolution of the power spectrum on this entire length scale that I've been describing, all the way from the adiabatic scales up to the gene scale, including the shape of the gene's suppression there. All you need to do is plug in the initial power spectrum of the field or the initial phase-space distribution of the particles, and this gives you an answer. I'll skip through this. Again, this is the same picture I've shown you before. These dots here could indicate point particles. They could be black holes, or they could be quasi-particles for wave dark matter. During radiation domination, you erase correlated fluctuations, but white noise is preserved. During matter domination, clustering happens. So now white noise doesn't quite remain. It grows, and you have gravitational clustering. But then there is a length scale below which you can't cluster, and that's the gene scale. Here is an indication that we've hopefully done the calculations correct. And again, this is we did along, so the solid lines are the analytic calculations of the power spectrum. You notice this adiabatic part on the left and the white noise part on the right, along with the gene suppression at large length scales. The dots are the results of simulations. So you see that it works pretty well, our calculation, compared to up to the point that we become nonlinear, because of course it's a linear, the calculation assumes linearity of density fluctuations. So you notice that up to this time, the gray region is nonlinear region. So it agrees pretty well for these simulation, with n-body simulations here as well. We can actually take our results for the power spectrum that we calculate in linear theory, and we can use a slightly fancy version of Press-Schechter-like formalism and predict the halo mass function in this case. Again, the solid curves are analytic predictions, the dots are from simulations, and they agree pretty well. So we hope that this also provides a tool into the nonlinear regime as well. And we've tried to compare the cases of just cold dark matter with white noise, our case that we are thinking about, adiabatic case without the white noise, but warmth, and adiabatic case with cold, and you can see the differences in levels of structure that forms on small scales in all of these cases. So it provides a nice unifying framework to doing warm dark matter with white noise, that is warm white noise, along with all the other cases that we are all familiar with. And up to the de Broglie scale, it also applies to wave dark matter that I was talking about before. And just quickly flashing that, the wave dark matter simulations after matter radiation equality also show these same features. This is going to come out hopefully in the next few weeks as well. These are simulations in the late universe that show both free streaming suppression and this white noise what white noise behaves as during matter domination with the gene suppression. Now, finally, if you go to very small length scales, then the wave dynamical effects, some of the wave dynamical effects become very important. These are things you cannot capture by just quasi-particles. These are things like solitons and so on that can form on very small length scales. Some of you that know me, I really love solitons. Of course, at some point, we have to make an appearance in any talk I give. So these are also things that are very small length scales you can talk about or even use these in the framework I've provided in the early universe to think about how these things will cluster. Okay, so it's about the right time to end the talk. So hopefully I've convinced you that by thinking about causality considerations, essentially, or just thinking about the assumption that dark matter is dominated by sub-Hubble field modes, you have a bound on the mass of dark matter particles of 10 to the minus 19 eV. And in the more recent work that we have been doing, there's a lot of fun phenomenology that arises when you think about both warmth and white noise together. And if you're interested, I can, of course, say more on either one. All right, thank you very much. Alex, you have a question.
Yes, yes. Mustafa, very nice, very interesting stuff, actually. I like your bound. Just a short question. So you, of course, assume that whole dark matter is just this ultralight particle. That probably would also allow you to weaken this constraint if this, let's say, ultralight gas is a fraction.
Right, absolutely. This is a fantastic question, Alex. And I was hoping somebody would ask, and of course, you've thought about it, so it's great. So the way to think about, certainly, in general, right, like, for example, neutrinos are warm, and it's not like